Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is actually to really tell you the definition of an inverse. And one thing I just tried to kind of hide away from last time, not get into, is basically the true definition of it. I showed you like how we could find them, but I never really defined what this matrix is doing, and there's a lot to actually what an inverse is. So an inverse is honestly, like, students always ask, like, can you divide matrices? And you can't divide them, but it is the thing, like, I'm going to erase this in a second. Like, if you have, like, this, matrix times a vector equals another vector kind of problem, in a linear algebra, like algebra 1 kind of thing, you literally do, okay, I'm going to divide by A, and then this cancels an X equals B thing over A thing. And so this is where the notation comes from, because this is basically like B times 1 over A, or B times A to the negative 1. But you don't divide matrices ever. But an inverse is basically as close as you come to basically being able to do that. So it's a very important thing. And in order to kind of do this at all, there is like some stuff actually linked to the determinant that we're going to talk about today. So basically today the plan is to give you the more formal definition of an inverse. But I want to start off and do this one kind of quick problem here. So if A is a square matrix and satisfies this, then show that A inverse equals 2I minus A, okay? So it's really just kind of a, like, more equation, kind of problem. So you're just sort of manipulating the algebra off of this equation right here. So given that, then you could move some things to the other side. Whoops, that is not what I wanted to move over the other side. I wanted to move everything but I. So I would be equal to 2a minus a squared, right? And now you can kind of do two things. Maybe I'll color code this. So you can either, you can factor a matrix expression like this, and you just have to make sure that you take it out of either the left or the right. So you can either write 2 times, like, if you take an A out on the right, then you're going to be left with an identity there. So 2 times the identity minus A, all of that times A. That's like one way to write that. Or you could take an A out on the left, and you're going to get A times 2I minus A. And so both of those, though, equal the identity up here, right? So now, if you look at what I have, right, this thing is now satisfying the, like, definition of an inverse. So I have XA equals AX equals I, where X equals 2I minus A. So 2I minus A, by definition, is a inverse, and that's it. And the square matrix part is linked to being able to do this too. So if A wasn't a square matrix, then you wouldn't be able to do some of the nice algebra right here. All right, so time to talk about the true definition of an inverse. And in order to do that, you need to know something called the cofactor and adjoint matrices, okay? And the good news is you actually already know what cofactors are, because you've seen them in this thing, the cross product. So the cross product is built out of actually cofactor matrices. So these are actually like determinants of cofactor matrices in the cross product. But these are like a cofactor, okay, just simply put, is basically the thing you get when you like cancel out a column and a corresponding row. Then that matrix right here, that one that's left over from the cross product, that is a cofactor. If you cancel this one and this matrix that's left over from this, and this is a cofactor matrix. So They're these things that are basically the leftover parts when you cancel out a row and a column. There's a lot more, honestly, I could even say about that, but these three things are cofactor. Technically, these are in the cross product. They are the determinants of cofactor matrices. But you're going to need those, okay? And just as a refresher, when you do determinants, right, there's like a sign pattern to the these corresponding matrix expressions here. So you get like positive, negative, all the way through. This is what it looks like for 3 by 3. This is what it looks like for 4 by 4. And that just kind of continues, all right? So the kind of just another example down here, you can do this along any row or column, actually. So if I use this kind of subscript notation where these are the entries, like in the first row, first column, this is third row, second column, that kind of thing, I can find a cofactor matrix in any spot, really. So if I do, they're calling it M22, which is like the matrix for this one, it would be A11, A13, A31, A33. And then this is just like more like talking about the sign of it and stuff like that. But don't worry about this stuff as much. It's not important. But you can just do it along any row or column. So cofactors are these determinants, okay, that you get by expansion, like not really expansion, but like Xing out any row or column and then doing the determinant of the resulting piece there. The cofactor matrix is the matrix that's built out of all those determinants, following the sign pattern. The sign pattern being the plus, minus, so on. So just to kind of do some, okay, so let's cancel. So A11, like the first cofactor, is the determinant of this. So 24 minus 0. That would go in the first entry, and it's going to be positive because that's how the sign pattern works for the cofactor matrices. Then if we do, let's just do another one. So let's do, how about this one and this one? So I'm basically expanding along this 0. So this would be A21. You have 2, 3, 0, 6. And since this started off positive, negative, positive, this is going to be negative, positive, negative. So this is a negative 1, right? So then I get negative 12, right? And that goes in there. And so you just do that for all these different ones, right? You could do another one where you do, this last one. If you go along the 6 there, that would be A33 and give you the 4. So you would, and it would be positive because it went positive, negative, positive, negative, positive, negative, positive, negative, positive, right? And so it's really just sticking in a 4. So that's the cofactor matrix, and the adjoint matrix is a fancy word for, they sometimes use ADJ of A. The adjoint matrix is the transpose of the cofactor. So this C is the cofactor matrix, all right? And so Cij, the cofactor matrix. And so the ADJ of that original A is you have to do the cofactor matrix, then you take the transpose of it. And so that's equal to Cji, right? Just flipping the I and the J. That's what the adjoint matrix is. So I know I'm not really explaining what they are. I'm just telling you their definitions right now. But this is actually the formal definition of the inverse. The inverse is 1 over the determinant of A times the adjoint matrix of A, where again A, the adjoint matrix of A, is built out of the transpose of the cofactor matrix, so Cji. So that is the inverse. And you can take entire, like, months of a linear algebra class and to analyze what this is doing and what these different cofactors do and all that. And if you're into that stuff, you should be a math major and you should study the theory of linear algebra. I really just kind of want to highlight a few points about this right now. And one of them is right over here. So I want to find the inverse of this matrix. And based on the definition here, I want you to think what must be true in order for us to compute the inverse, right? So let's start with this, actually, because this is kind of easier. So determinant of A being in the bottomless fraction means that in order to construct the inverse, we need the determinant of A to not be 0, right? It just makes no sense to do 1 divided by 0, so we need this to not be 0, okay? And the determinant of a matrix, a 2 by 2, right, is, so let's actually like just do it for my A up there. The determinant of A, B, C, D, right, would just be equal to AD minus BC. So I need, just to be a little more clear for this specific problem, I need AD minus BC to not be 0, all right? And so if we use the definition of this is the formal definition of an inverse, with this piece in here, which is my determinant, right, I can actually write the general formula for the inverse of A. So I'm going to start off and do all the cofactors. So I'm going to keep with the notation capital A11, A12, what was it? 21 and A22. So these are the cofactors, which again, sorry, I went too far. So I'm talking about these kind of things. And when you do cofactors of a 2 by 2, you're literally looking at a 1 by 1. So you're like A11, the cofactor of this part right here is you just blank this out, right? And you get D, and it's literally just positive, right? If you do A12, you blank out this, and you get C, but it's negative. Then if you do, erase again, so blank out, you get B, and it's positive. And then, what color am I not using? This one. So then you blank out that last one, and you get negative A, okay? So my matrix of, my cofactor matrix, right? Cofactor matrix, I'm going to call it Cij, equals that thing. And then the adjoint matrix is the transpose of that. So it's equal to Cji, or just cofactor matrix transpose, which would equal that, but I just realized I made a mistake because over here I messed up my signs. It goes positive, negative, but that's like going across positive, negative, and then I should have started negative, positive, and just because I was just going down, I like got off with my signs, so I should have gone positive, negative, negative, positive. It should look like this. Positive, negative, negative, positive. So this and this the signs need to switch there. So I've got negative B, negative B, negative B, and then A is supposed to be positive. So there we go. Okay. So now I can basically go and plug in my formal definition. So I have A inverse is equal to 1 over the determinant of the matrix, which in this case is literally AD minus BC, and then it's times D minus B minus C A. And if you look up the inverse of a 2 by 2, a general 2x2, you will see this formula. And again, lots to say. I wouldn't bother memorizing this because in practice, what you're still going to do is basically you're going to deal with such big matrices that you just go to your calculator and you plug this in. But like you will run into 2x2 matrices sometimes, and if you do, I usually use this, but it's one of those things where more like you use it enough with 2x2s and then you just start remembering it. It's not something that I would say like is as important as like the quadratic formula right now to memorize. So, but that is it. That is the inverse matrix written out symbolically for a general 2x2. And so I just thought I'd show you kind of how we could use this in a problem that should make a lot of sense. So we have a matrix we could form out of this 1, 2, 3, 3, 4, -2, right? And this matrix, we can think about it as some matrix 1, 2, 3, 4 times like a variable vector equaling 3, -2, right? And if I let this just be like, I don't know, a for a second, and like x and like some vector b, then basically what we're going to use the inverse for is we can do a inverse multiplied on the left, and we have to multiply on the left right here, and then these would cancel, and you would get x equals a inverse b. So basically, if you can find a inverse, you could just do a inverse times this 3, -2, and you'd have the answer. So now that you have a, and you have your little formula over here for a inverse, you could go and plug everything in and get the answer, like using this. So 1 over, so the determinant of this is, let me just do that, determinant of a is 4 minus 6, which is -2, right? So 1 over -2 times, and you basically just have this d minus b minus c a, which would be that. And then we're going to multiply it by, so this is my a inverse, right? All of that part. And then b is 3, -2. And if you just like crank that out, okay, you're going to get 8, sorry, and 5.5. And so this is truly, the x and the y that solves this system. Now, again, I'm just doing this to kind of show you like how we might use the inverse to solve this problem, but like most people would still just go and like plug this into a calculator and get an answer. But that is what the inverse here is really doing, and we can use it in problems like this if you wanted to. You could just solve this problem instead of going to your calculator and like plugging everything in.